In this section, we continue our journey on the central limit theorem. And instead of sample means, we're now going to discuss sample proportions. So there's a few things that we have to kind of talk about. First of all, we really haven't touched sample proportions, only in the sense of probability. So we're going to have the central limit about sample means and then sample proportions. And the idea is quite the same. It's like you're just taking a bunch of sample proportions and taking the proportion of the proportions, and the concept doesn't change, just the problems do. So we're going to do the exact same thing, except all we're going to have are proportions. So what is a proportion? A proportion is exactly what you think. It's a certain amount of the number of whatever attribute over the total number in the sample. So how many people have brown hair over the total number of people that I have in my sample. We denote a sample proportion as p hat. And we denote the population proportion as just p. So p hat means sample and p doesn't. So p means population. So what I would think is if x bar, like it's similar to x bar, right, was the sample mean. So if p hat, so something on top of the letter would denote the sample, right? Okay, so let's just do a quick example of finding a sample proportion. So in a Quinnipiac University poll conducted in May 2008, 1,745 registered voters nationwide were asked whether they approved of the way George W. Bush is handling the economy. Of the 1,745 registered voters, 349 responded yes. Obtain a point estimate for the proportion of registered voters who approve the way George Bush is handling the economy. Okay, so the sample proportion is always x over n, and recall that x is given as with the specific characteristic, and n is the total in the sample, right, the sample size. Sorry. Sample. There we go. So if we're looking for the number of voters that approve, the number of voters that approved were 349. So here we're going to have p hat equal to 349 over the total number in the sample, which is 1,745. Now remember that the fractions could be in decimal as well. So this would be 0.2, and then you could always rewrite it as a percent as 20%. It just depends on what they ask for. But when they say to find a point estimate, the point estimate itself means to find a sample mean or a sample proportion. Okay, so what do we know about proportions? Since this is the first time we've seen it. Well, the sampling distribution of the sample portion actually is pretty much the same as the averages, except we're doing proportions. So notice that it says if a sample n increases, the shape of the sampling distribution becomes approximately normal. The center where we used to put the mean is actually now the population proportion. So we actually take the mean of a sampling distribution with sample proportions to be the population proportion. And the spread is the same, right? The sample proportion decreases as the sample size increases. So it's going to be, the formulas are going to be similar. And again, these are all on your formula sheet. So let's go ahead and take an example. According to a time poll conducted in June 2008, 42% of registered voters believe that the same-sex couples should be allowed to marry. Describe the sampling distribution of the sample proportion for sizes of n equal 10, 50, 100. So notice again, it wants you to talk about the sampling distribution. So the sampling distribution in this case for proportion, right? So distribution, right? We would discuss prior, right, to the mean and the standard deviation, but we're not going to do it now with respect to the sample mean. We're going to do it now to the sample proportion. Okay, so let's go ahead and do that. So the first thing we'll discuss is the mean. So the mean of the distribution, abbreviate, is equal to the population proportion. So this means that mu sub p hat is equal to p, and they said that the population proportion that believed in same-sex couples should be allowed to marry was 42%, right? 0.42. So that just means that the mean with respect to the sampling proportion, the sample proportion is 0.42. All right, so the next thing we want to discuss is as n increases, right, n goes to infinity, the standard deviation decreases. And that makes sense because you can only assume we're going to divide by that square root of n. So is as n equals 5 to 10 to 100, we expect sigma sub p hat to decrease. And because we assume the sample size will be large enough, we do expect the population proportion to resemble p hat, the sample, right? Because again, if we take enough samples and enough averages of the averages, it becomes the population average. Well, that's similar with proportions. So these are the three things that we're going to discuss when it talks about sampling distribution. We'll always have the mean with respect to the sample proportion as the population proportion. And our standard deviation, we can only assume that as my n increases, that this will decrease. And that means that we'll probably end up dividing by that square root of n somewhere. Okay, so let's move on to the sampling distribution of p hat. So prior, remember with the means, we said, how do we know something is normal? Right? Well, they'll either tell us or what? Right? For x bar, we just needed n to be greater than or equal to 30. Well, that doesn't make sense for us now because with proportions, it's always going to be, proportions will always be, you know, between 0 and 1. So how do we determine if they don't tell us that the population is normal to be able to assume that the population is approximately normal? Well, not to worry. Mathematicians always have tricks up their sleeve. So we say that the shape of the sampling distribution is approximately normal by calculating, and we discussed this in the binomial distribution section, chapter 4 or section 4.3, a little bit towards the end. And essentially, you take the sample size and the population proportion and multiply it by the complement. If this value is greater than or equal to 10, you have it. Like, so you can assume that your population is approximately normal. So this is going to be a condition we're going to meet, and this will be our 1I when we do our problems. The second part is to discuss the distribution, right? So like I said before, that the mean of with respect to the sampling distribution with proportions is the population proportion, and the standard deviation is the square root of the population proportion times the complement over the n. So there's the square root of n. Okay, so now then you ask, you're like, okay, that's great that we have this, but then what if we do this and it's less than 10, like if it's 9 or 8? Well, don't forget, we love binomial, right? Binomial distribution is so awesome. Okay, I say this because look, we're in a different chapter, we're doing something totally different, and yet we go back to the binomial distribution to give us a hand when we need it, right? So binomial distribution is very powerful, and that section is really powerful, and we're going to be using this binomial distribution whenever we have this. So if we aren't given that the population is normal, we do this calculation as less than 10, we always go back to binomial distribution. And this is for the rest of the class. We only hope that we have this relationship, right? Because then we don't really worry about other concepts. But here, if that happens, don't worry, you do have a trick up your sleeve, so make sure you highlight that. So now, let's do a little bit more with that time poll. And it says, according to a time poll conducted, right, 42% of registered voters still believe that the same-sex couple should be allowed to marry. So now let's go ahead and take a random sample of 50 voters and determine which voters believe that same-sex couples should be allowed to marry. Describe the sampling distribution, right, and so when they say sampling distribution, remember with the sampling distribution, they want you to describe the mean and standard deviation with respect to the distribution. So the first thing I want to do is go in order, right? So the first thing we'll do is we have to go ahead and see whether or not it's normal. Because we can't say a random sample is 50 is larger than 30 because we're not doing that anymore. We're doing proportion. So we have to do the NP times 1 minus P and check if it's greater than or equal to 10. So we note that N is going to be equal to 50, right? And the population proportion we noted in the previous example is 0.42. If I took 50 and multiplied it by 0.42, and multiplied it by 1 minus 0.42, would it be greater than or equal to 10? I don't know. So if I went to the calculator and did 50 times 0.42, and then you can go ahead and just put a parenthesis and 1 minus 0.42. You don't have to, you could do it all in one line. We get 12.18. And this is greater than or equal to 10, so we can assume normality. Awesome. And that's all you have to do. The second piece, right, is to make sure that the sample size n is no more than 5% of the population size. So this means that n can be no more than 0.05 of capital N. So, and this is what it's saying. It's saying the population is size n, and then you took a sample of little n. So this comes from up here, and I like talking about this first and then coming up here, because it talks about when you're sampling from a finite population, you want to assume that your sample size is no more than 5% of the population. And regardless whether or not that your product here is greater than or equal to 10. It's really important because that way we understand that the sampled values are going to be independent, and we know that we're verifying we're sampling from finite populations. So in this case with voting, we have to think about the sample size n. If n is equal to 50, is this less than or equal to 5% of all registered voters? Well, think about it. Is 50 people, 50 people is maybe your biology class, right? Do you think that's going to be less than or equal to 5% of all registered voters in the United States? I think so. So at this point, you'll need some common knowledge, and we usually assume this holds for this class. It's only when you really get to research methods that you're going to have to pay really close attention to this criteria. So I would say 50 people is definitely less than 5%. Yes, right? So with proportions, you will always go ahead and make sure that these two criteria are satisfied. And notice we haven't even got to the distribution yet. So this is kind of like part one. And then the part two part is the sampling distribution. And so now we can go ahead and talk about the distribution. I wouldn't want to talk about the distribution if this was less than 10 or this didn't hold, right? The second one, because then the distribution turns binomial if it's less than 10, right? So there's just some things that we want to do beforehand so that we can actually talk about the distribution. So the first thing about the distribution would be mu sub p hat, right? So since we know that p is equal to 0.42, and we know that this is we can assume normality because this criteria was satisfied, that the mean mu sub p hat is also equal to 0.42. The second part is the standard deviation. So because the standard deviation is given to us as the square root of p, 0.42, times 1 minus p, 0.42, divided by n. And in our case, n is 50. So maybe hit second x squared, and then I'll go ahead and grab that. And we get 0.0698. That is the two parts that we have to do for this section. Proportions is a little more involved, but before you even start a problem, you're going to have to make sure that it's normal, meaning this product is greater than or equal to 10, and ensure that the sample size n is no more than 5% of the population for whatever scenario. Then we can discuss the distribution, and from there, then we can go ahead and color the graph, find the probability, and use our calculator. But it's going to be building. We're going to be building from this, and you can see that it's getting a little bit more intense, right? We're doing a lot more criteria before we actually start a problem.